Thank you for clicking on the introduction and overview to the St. Joseph County Residential Septic Pump Spreadsheets. In this video presentation, I'm going to talk about the residential septic pump spreadsheets that I created at St. Joseph County, and to give you an overview of their purpose and some of their intended use, some of the nuts and bolts, and this approximately 30-minute video will be posted just for introductory purposes, and then we're going to post another video with some worked examples. And so let's kick off this presentation. Again, my name is Matt Gavelik. I'm with St. Joseph County. I'm a professional civil engineer specializing in the fields of water resources and environmental engineering. I have a background in a little bit of lift station design in Indiana and actually the nation of Libya. And so I've created at St. Joseph County basically 3 different spreadsheets: flood dose spreadsheets, pressure trench spreadsheets, and elevated sand mound spreadsheets. And these spreadsheets, the function of them is essentially a user can put in 2 to 4 minutes worth of input data, and the spreadsheets will automatically analyze the operating point of the system, and then we'll take that operating point and we'll check it against state code compliance, against Indiana Administrative Code 410-6-8.3. And it'll take and comply with, it'll check for compliance with that code, and then it'll offer suggestions as to what to do if it does not meet the code requirements. This spreadsheet has taken quite a bit of time to create, as you can tell once we start getting into it, and the intended purpose of it was really to be given to regulators across Indiana, local health departments, county health departments that will use the spreadsheet to check pump design. It analyzes things precisely and probably better than any spreadsheet that's been created in Indiana for this purpose. And so it's to be given to county regulators, but we also are encouraging this to be distributed to designers throughout Indiana so they can check their designs before they submit it to local health departments. Okay, so I'm going to get into today in this introductory and overview video the 2 methods, the previous method of the design point method and the operating point method, some of the facts about the spreadsheet. I'm going to go through an example and show how this spreadsheet helped catch something that wasn't in code compliant that we probably wouldn't have caught without using the spreadsheet, some of the benefits of the spreadsheet, and how we're going to go forward from here. Okay, essentially there are 2 methods of pump selection. On a macro scale, these really are the same method, but as you can see on the screen here, and let me get out my pointer with a pen. Okay, we have here a design point method and the operating point method. And these 2 methods, like I was saying, are pretty much the same method, except the design point method is one iteration. It's only one calculation of the operating point method. And as most of us are familiar in Indiana, to utilize the design point method, we find a flow rate that we want our pump system to operate at, and then we calculate the total head that's imposed on the pump. And from there we get this design point. And then most people then find a pump that is larger than, it's sized greater than that design point, which means it's to the right and up of that design point. That design point is part of a system of points called a system curve. As you can see here, it's that same design point, but the design point does not actually show where the system will perform at. What describes where the system will perform at is the operating point, and that, as shown here, is the intersection of the system curve and the pump curve. Okay, so let's do a quick comparison of these 2 methods. You can see here I've made green and red the pros and cons of the design point operating point method. The design point method is great because it only requires one calculation. That was they were created essentially before the use of personal computers, and so one calculation was a great benefit. However, the design point method is an approximation, whereas the operating point method is precise. You actually find out where the pump will be operating. The design point method is open to interpretation. Some people could say, well, it's close to the curve, it's far from the curve. You know, who's to say which is close and what's far? Whereas the operating point method, if you use it, it's non-debatable. It operates there, and therefore it meets code compliance or it doesn't meet code requirements. The design point method, therefore, code checks that are applied to a design point are simply a guess. They're not actually precise like the operating point method. The negative of the operating point method is that it requires many calculations. However, one can create a spreadsheet that would essentially make no calculations, or the user would have to do no calculations to use the operating point method, and that's what I've created here. Okay, let me go into a little more detail about what the operating point method is. Like I said, it's the actual performance of the system. It's the intersection of the system curve and the pump curve, as shown on this picture. And the pump, as I said earlier, it only operates at the operating point, not the design point. Okay, so what is a system curve? A system curve is the pressure or head. Head is a term that is used to describe pressure. It's the amount of foot that a column of water will rise under a certain amount of pressure. So they're kind of synonymous terms, different units. The system curve is the amount of head or pressure the pump needs to push against at various flow rates. Let me describe that in an example here. Let's say you have one pipe that's an inch in diameter, but it's 2,000 foot long. If you were trying to push fluid through that, you would need a lot of pressure to get it all the way to the end of the pipe. Whereas if you had a large pipe that was only a foot long, it wouldn't require much pressure to push water through it. And so a system curve is really describing the amount of energy you have to put into water to get it to go through your system, whether that's a flood dose system, which is just a force main to a distribution box, or a pressure trench system, elevated sand mound that goes from a force main into laterals and has to pressurize the laterals. Those systems require a certain amount of energy put into it, and that's described by a system curve. So a system curve is a graph that shows the amount of total head. Like I said, head and pressure are synonymous, so total pressure. It's also called total dynamic head because it's moving. These are all pretty much, for this application, synonymous terms. This is hard to do by hand to calculate a system curve, but it's easy with computers. The total head can be calculated by three main components. And let's consider a flood dose system here. The flood dose system curve is only comprised of two main components, and that's the elevation difference and the friction loss in the pipe. Now the elevation difference, as we know, is the difference between the highest point of the force main. Usually it's a distribution box, but sometimes a force main could go up higher than a distribution box. That would be the highest point, to the pump off elevation. That elevation difference represents the amount of head that you need to push the water up. But then you also have, as shown here, the friction loss. Now this friction loss is not just a lump sum amount like the elevation difference. This changes with the flow rate, as represented by this graph. The more flow you get, the higher velocity you get, the greater the friction. Now with a pressure distribution system, pressure trench or elevated sand mound, there's really three components. There's the elevation difference, which is calculated the same way as a flood dose system. But then you also have the friction loss. But then we add in another component called the inline residual pressure head. Other states or agencies call this operating pressure. it's the pressure that the laterals need to operate at. And this, as shown by this little chart, shows that it's also not just a constant number, it changes with the flow rate as well. So these are kind of complex equations. Well, they can be complex. They're not as easy as just one calculation, but with a spreadsheet, it simplifies this calculation process. Okay, let's talk about what a pump curve is. A pump curve represents the height that the pump can lift a column of liquid at certain flow rates. Most of us are familiar with pump curves. Basically, they're specific to each pump's design, based on a pump's motor, based on a pump's speed, based on the impeller size and shape, volute size and shape, etc. So here's an example of some various pump curves. As you can see, there are different models here, and the pump curves look different because each model is different. So a pump curve is unique to each pump and is available from all manufacturers. If someone made a pump, they have a pump curve for it. Okay, so that's basically the two different methods. An explanation. The design point method was powerful before the use of computers, but with personal computers, we can create spreadsheets that will simplify this process. And so I'm going to go into some detail now about the spreadsheets I've created. Like I said, I created 3: flood dose, pressure trench, and elevated sand mound. And it takes about 2 to 4 minutes to input the data. In the next video, I'm going to show you how to input some actual data. It'll take a little bit longer because I'm actually going through and explaining all these steps. These spreadsheets require little understanding of Excel. It works with version 7 and up, so version 7, 10, 13, and whatever comes out in the future. And one of the real powerful aspects of the spreadsheet is that it has pre-programmed pump data. So I have painstakingly went to many pump websites and pump manufacturers' websites and taken their pump curves and put them into this Excel spreadsheet in numerical form and fit curves to them and put the curves into the spreadsheet. It also has the power to enter user-defined pump curves. So if you don't want to use one of the pumps that I provided in the spreadsheet, then you can go and find your own pump, and all you have to do is input 7 data points from that pump curve, and it'll work in this spreadsheet. Okay, as that point just stated. With that said, though, I would caution everyone to verify the pump curves. I would verify it to make sure it's current with the manufacturer's pump curve that's listed on their website. Another thing you'll want to do is you want to make sure that the curve that's shown on the spreadsheet isn't wavy. And you'll see most of these curves look very smooth. If there's one that looks wavy, then I would ignore that or not use it. For instance, if you used a user-defined pump curve and you put in 7 data points, and some of those data points were just wrong or out of place, then the curve will look really wavy. You don't want to use that curve. Another thing to check to make sure the pump curve is correct, make sure that the R² value is greater than 0.97. And you'll see in the next video that I make, there's a little R² term in the chart, and the R² term describes how the curve fits the data points. And so you want an R² value of 1, but 0.97 and above is excellent. Okay, so in the spreadsheet there are 4 worksheets, and those are tabs. Let me open up one of the spreadsheets here, and okay, and you'll see what I'm talking about. Okay, so there's 4 tabs at the bottom, and the first tab describes, or the first tab is for the user agreement and some brief instructions. The second tab is for the actual data input analysis, the code compliance checks, and recommendations. as you can see here, here's the README first tab. So I made that pretty clear. You always have to start with the README first because a spreadsheet won't allow you to do any calculations unless you accept the hold harmless agreement, the user agreement. And then the second tab is the design check tab. And as you can see on here, it says you must accept the user agreement to proceed. Then there's a help tab with lots of info, and I'll get into that later. There's a calculations tab, and this has lots of info too that are not pertinent. It's basically the working engine of the spreadsheet. It's where the magic happens. So, okay, let us continue. Okay, another thing that I want to point out here is that these spreadsheets I created, they go about calculating the inline residual head a little bit differently from what most of us are used to in Indiana septic design. Okay. Typically, most of us, when we think of the inline residual pressure head, we think of an automatic 3 feet of head, and that goes into our total head equation. However, just because we put an automatic 3 foot of head into the equation doesn't mean that'll actually happen when it operates. And that's kind of the power of this spreadsheet, because it's considered a lot of these engineering concepts. The inline residual pressure head is actually a byproduct of the number of holes in a system and the operating point of a system. So if you want 3 foot of head in your laterals, your operating pressure to be 3 foot of head, then you need to write it into your system and performance of the pump. So it's not writing it on a sheet of paper just for the total head calculation. It's that I need to make sure that my number of holes in my laterals are the right amount and my operating point is the right amount to give me 3 foot of head. Therefore, these spreadsheets actually you don't enter the inline residual head as an input. It's actually an output of the spreadsheets. It tells you what the inline residual head is based on the number of holes that you have and the operating point. Okay, so this basically describes what I'm talking about here. There's 3 factors for the inline residual head. That's the operating flow rate, the number of holes, and the hole size. However, in Indiana, we make sure that the hole sizes are only 1/4 inch. So that's really not a variable. So here's a little description, 2 graphs that show basically if someone were to use the design point method, they would pick a point and a pump that's above that, but they're not actually finding the operating point. So they say, okay, I've got 3 foot of head, and they just put that in the total head equation, and to them they're thinking they have 3 foot of head. But when you actually, here's the design point, when you actually go up to calculate the system curve and find the operating point, you find that your flow rate is different than what you thought it was with the design point method. And so your flow rate in this example, this fictitious example, it's actually 10 gallons per minute greater, which resulted in an inline residual head of 3.8 feet as opposed to 3 foot of head. So if someone with the design point method put 3 foot of head into their total head equation but didn't actually find the operating point, then it's guaranteed that their inline residual head is not correct. And so that's another power of the spreadsheet, is that it'll tell you what the true inline residual head is, and it'll allow the regulator to say, yes, that's acceptable. It'll allow the designer to say, I want that or I don't want that, I want to change that, and it actually analyzes it truly. So let's go through a flood dose example. This is an example from a very experienced installer who submitted a flood dose design to me at St. Joseph County, and he used a design point method like we all do. Notice right here where his design point is it's not on the curve. So I knew when I first saw this that, okay, I want to find where this is actually performing. So I plugged it into my spreadsheet. Let me give you a little background though. It's a 4-bedroom house. So he went to the Indiana Code Table 7, and of the gallons per minute flow rate allowance, he used the 60, the highest end, and he used a 3-inch force main because he said he likes larger lines for a larger number of bedrooms, and he picked a pump that's above the design point. So he did everything that seemed right. Does this comply with code? So I plugged it into the spreadsheet, and like I said, in the next video I'm going to go through some actual examples. I'll go through this example of how to input the data, but that's real briefly what it looks like. And then it analyzes the spreadsheet. After you put that data into it, it automatically analyzes your operating point and the system. So here we have the design point that he submitted. Notice that it's part of the system curve because it's one point of many. But then the actual operating point is all the way over here. So the spreadsheet is saying the operating point is 71.3 gallons per minute, but what he submitted was 60. Okay. Now, there's that difference, but then there's also something I want to point out here, and this is something that Alice Quinn has talked about at ISDH conferences, that pumps have a sweet spot. A sweet spot is where the pump likes to perform. It's really designed to perform in that range, and that's usually the middle half, middle third of a pump's performance curve. Okay, this area right here. And a pump that operates right in the middle of its performance curve actually draws less energy than a pump that operates right here on its extremity. From this manufacturer, Zoller, they actually don't publish their efficiencies, but what I would guess is that there's maybe a 10 to 20% difference in efficiency between the middle of the pump curve and this extreme edge. So really over time, let's say you had a pump in a homeowner's property for 10 years or so, the amount of energy they're using is quite a bit more when it operates outside of its sweet spot, that middle half, middle third. Another problem about operating outside in the extremities is that it actually reduces the pump's lifespan, the longevity of the pump. Okay, so that was a little sidetrack, but let's take a look at what the spreadsheet analyzed as far as code compliance. So here we can see that it got 4 yeses and 1 no. And yeses are green and filled in green, and the no's red with red filling, so they stand out quite a bit. You can see here that it checks that it supplies the correct dose amount in 1 dose, and so that's the volume, the daily design flow plus the drain back. And the spreadsheet asks you questions for all sorts of information about drain back. It can go to the field, it can go to the dose tank, it can do some sort of both, or it can remain underground, at which it would, if it actually didn't drain and just stayed level under the ground, then the spreadsheet also asks you about freezing and what county it's built in and checks it against that. So we've really considered everything when we looked at this. But we see here that it says, no, it's not meeting the flow rate requirement. And as we saw earlier, it said that it's actually performing at 71 gallons per minute. We see here that it's a max of 60, so he's outside of that. Now, another powerful thing about the spreadsheet, not only does it check for code compliance, but it also checks for general engineering design. And for this flood dose example, we have 2 engineering design checks, and that is where the pump is in the actual performance curve, like I was talking about earlier. Is it in that sweet spot? And this one says no, it's not. It's in the outer 5% extremity, so it's saying you need to redesign this. And I gave in the coding of the spreadsheet a lot of liberty to the designer, so that really only the outer 10% is worthy of a redesign. Everything else is poor and fair and good and excellent. So another check it does is for a pump runtime. And usually it's just standard lift station practice that your pumps run for 10 minutes or more. And here we can see it's not running for 10 minutes. There are a lot of manufacturers that say it's okay to go underneath 10, and there are some that don't. So it's something to look at and to consider. That's another thing that's a power of the spreadsheet. We'll see later in an example that for elevated sand mound and pressure trench systems, the run times are often very little. And so this spreadsheet will actually tell you how long the pump will run for. And so you can check with the manufacturer, you can check with the designer and say, do you know that your pump, you're designing it to only operate for a minute and a half? Or, I had one in St. Joseph County try to do it 15 seconds runtime, and I said that's just not possible. You need that runtime for the motor and the pump to perform well long term. Okay, I just talked about all that. So from designing lift stations and whatnot, I knew when I saw the system curve that it was very flat. I thought, you really need to look into a smaller force main, and that's what will bring the system curve up quicker. And so I talked to this designer and explained to him what was going on. I said, try a 2-inch. And here's what a 2-inch looks like. And again, this is another power of the spreadsheet. All I have to do a whole new design is that I just have to click on the force main size and go from 3-inch to 2-inch, and boom, everything automatically updates. It checks for all code compliance and does that all right away. So as we can see here, it's actually now is it within the pump sweet spot. The curve went from a very flat, kind of like that, up to a sharper curve, and it operates a lot better than it did before. Notice the operating flow rate is less than 60, so that looks good to me. The automatic code check says everything looks good, and it says that it's operating within a fair range of the pump's performance curve. So that's great. The runtime actually went up above 10 minutes, so we've got all green lights here. So I explained this to the designer, and he resubmitted a version with a 2-inch line. And let me actually write on here, this was a 3-inch and this is a 2-inch. And so we can see here his design points that he submitted. Notice he understood the operating point theory, and so he got a lot closer to the curve here. And we can see here his submitted revision is code compliant, it's a better design, increases pump longevity, and it's more efficient than the previous one. And all that came from 2 to 4 minutes of inputting info in this spreadsheet. Okay, so let's talk about some of the general benefits of the spreadsheet. As we saw in that example, it'll produce better designs. Really, one of the best things is we encourage counties to actually email this out to your contractors. The contractors that do pump design in your county, send this to them and say, hey, look, we're going to start checking for this. If you want to see what we see before we see it, you can use this spreadsheet and see if it meets code compliance. And that'll save time by eliminating resubmittals. It produces better designs because it utilizes the operating point method, which is a more precise method. Also, it's going to produce better designs because we're going to be checking for other engineering checks that are not in code. And here in St. Joseph County, we've decided to not necessarily say that all pumps fail if they fail those engineering checks, but they're flags that are raised, and then we look into what can we do differently, and we'll usually let the contractor know. And each county, if they want to, they could write into their ordinance, we want a pump that operates in the middle half of its pump performance curve or whatever. Okay. Yep. Made those points. with the pressure trench and elevated sand mound, it will go through lateral and manifold sizing checks. So that's a real benefit. Another great benefit of the spreadsheet is that it actually calculates the effluent velocity precisely. So, why do we need to calculate it precisely? Well, as we recall in the code, on that friction table, that pipe friction table, they say at the bottom that the effluent velocity cannot get beneath 2 feet per second. 2 feet per second is the resuspension velocity, meaning the velocity that it takes to keep solids in the fluid from settling. So if it's moving faster than 2 feet per second, it's going to keep those solids flowing and they won't clog up the line. So it's very important that the velocity is above 2 feet per second. And so the spreadsheet also watches out for large velocities. Between the velocity of 5 feet per second and 8 feet per second, it says, verify that the force main can handle such high velocities, and above 8 feet per second it says you can't do that. And I'll explain a little more in the example video why we recommend that. The spreadsheets will save time. It just requires 2 to 3 minutes of input, and it performs all calculations instantly. It performs all checks to Indiana code instantly. You can see with the elevated sand mound, that's 14 checks that it just does for you automatically. And it also offers recommended solutions. And I've heard some feedback from other counties that they like this feature. Let's say, for example, you have someone in your county who is new to septic pump design, and they don't feel comfortable recommending to a designer to change something. Well, if they don't feel comfortable, all they have to do is go to this tip column, and you can see this is from the example we looked at earlier. And wherever code compliance is failed or general engineering design is failed, then a tip cell pops up, it appears, and it gives you recommendations for how to improve that. So you could literally copy and paste that, and that's come from I've written these tips, so it's coming from a professional engineer, but it also comes from ISDH staff who have reviewed these and offered their recommendations. So again, this is going to bring a lot of education. It'll give users a working knowledge of pump hydraulics. Another educational benefit of the spreadsheets is the help page. Remember how I said there are 4 tabs at the bottom? There's one for, it's called help, and there is a lot of good information. Here's some excerpts of what you can see in the help page. Unfortunately, I spent way too much time working on this, probably about 70 hours actually writing this help page. So there's color-coded worked examples. You can, if you're curious what the actual horizontal length of pipe is, here's a color code. Horizontal length is 5 feet per second. I'm sorry, is 31 feet. I'm still thinking velocity here. So if you want to know the Hazen-Williams equation plus the inline residual head equation, and you want to really get nerdy and spend a whole Saturday just digging into equations and whatnot, then you can take a look at the equation that I wrote out and that the spreadsheet utilizes, and it lists beneath it every one of these variables and where they come from. So there's really a lot of information in here. It's great for training, and someone could just sit down and just learn a lot about pumping hydraulics just from reading this. Okay, so that's an intro to the spreadsheet. Let's talk about what it'll be used for and going forward. So, here in St. Joseph County, we've started implementing the spreadsheet. We check every pump design with a spreadsheet, and we'd like to encourage other counties in Indiana to use this as well. They're free. They're for the public. We thought if we were going to make them for ourselves, why not make it in such a way that it's available to the whole public? We recommend that you distribute them to the contractors in your county, as we will. And we've heard feedback from quite a few contractors who are excited to use these spreadsheets. They said that it'll really speed up things for them. And also ISDH will email the spreadsheets to local health departments. They will post the spreadsheets on SharePoint, and they'll also email this video or post it on SharePoint. So that's how the word is going to get out. Just another side note with the Help tab, about 99% of all questions can be answered on the Help tab. It may be easy just to say, well, I don't understand what's going on, and just minimize it. But if you go to the Help tab, every single bit of information that the spreadsheet asks, checks, analyzes, whatever it does, it's explained in detail in the Help page. So you can go over to there and find out most of the answers to your questions. If you happen to have a question that's not in the Help tab, then Alice Quinn, the sorry soul, has volunteered to answer questions. So her email is listed on here. She's with ISDH in the Northeast region. Okay, also, just to let you know, the Sewage and Sump Pump Manufacturers Association is reviewing the spreadsheet. And I want to also say a special thanks to Mark Nelson, who is the director of St. Joseph County Environmental Department. Without him letting me set aside 140 hours to create this would not have happened. He's also set aside county time to be distributed throughout other counties in Indiana, so that's been great. Dr. Don Jones of Purdue Ag Engineering, he reviewed the flood dose spreadsheet, the engineering engine behind it, and I appreciate his input. And also Alice Quinn has reviewed it, provided quite a bit of input throughout, and I appreciate her hard work. Okay, and last but not least, we will put the spreadsheets and videos on the St. Joseph County website, which is found here in this hyperlink, or you can just type in St. Joseph County and go to the Health Department Environmental Division, and you'll find it that way. So I appreciate your time, and stay tuned for the next video, which I'll go through 2 examples and talk about some of the general